Right, so welcome back to Dr. Carl's Society Machines, still on physics. Now, let's look at elasticity. Okay, so elasticity, let's look at that. So let's say we have wire, a metal like this. Metal like that. Okay, and then we stretch it like this. When you stretch it, and then it comes back, then we say it's elastic. Okay, any material. Okay. Now, as you keep on stretching it, it comes back, still within the elastic. At the point when you stretch it, it doesn't come back, it stays as it is. So from the point that it stays as it is, then you say it has reached the plastic region. So this is the elastic region, this is the plastic region. Okay. Now at that point, as you keep on trying to stretch the wire, you may hear a kink sound. A kink or a sound. Sound is just telling you that the molecules are no longer returning but are sliding on top of the other. Okay, and that kink sound, we call that point the yield point. The yield point. Okay, so beyond that, you keep on stretching, until at the point where we get to the end of the plastic limit, or plastic deformation. Elastic deformation. This elastic region or elastic deformation. At that point, any further pull will cause the metal to break. So we get to the breaking point. Now, once you get these principles, it will be easy for you to have the graph where you can plot stress against strain. And then sometimes it's also extension against stress, all these ones, right? Now, so what we can recall from here is that we usually will have the elastic region, then we move to the plastic deformation region. Okay, within the elastic region, there's a portion where the force that you apply to stretch will be proportional to the extension. Okay, and that part we call the proportionality region. The proportionality region. Okay, so the proportionality region is within the elastic region. Just a little beyond the proportionality region, you can still have elasticity, but when you pull, the force of the extension due to that force will not be proportional. Okay, will not be proportional, so there will be a change. It will no longer be proportional. Okay, although they are within the elastic region. Then at the point, at the end of the elastic region or the elastic limit, you have the plastic region beginning. At that point, that is where you have the molecules of the material sliding on top of the other. When they slide, they don't return. At that point, you have the plastic deformation region. Okay, and so you keep going, such that at the point this comes here, it separates from this one, and that is the breaking point. Remember where the sound, you hear the sound of the slip is the yield point. It's not the same as the breaking point, it's different. Alright. So these are the points I want us to know. So when you have a graph shown like that, then it goes up, you can actually tell where the elastic limit is, where the breaking point is usually at the end. So you have up to this point, this is the plastic region, and this is the elastic region. Okay, and so you have the proportionality region here, still within the elastic region. Okay, then there are just some few points away from the plastic region, you have the yield point. Okay, so you don't need to memorize these things. Okay, in between we have C, we have the tensile strength. Okay, so this is looking at the stress, and then the strain. Of course, we have defined stress. Let's look at some basic things to. Right, so let's look at some definitions here. We've already stress is given by force per area, okay? The cross-sectional area, okay? The force that you are using, the cross-sectional area. So we have that area, and there's a force pulling it, okay? The force per cross-sectional area, that's your stress, okay? Now when let's say you have this and you stretch it to this point, there's an extension. Okay, so this is the length. The extension per length is what we define as strain. So if the force pulls it and is able to cause an extension of the length is what we call strain. Okay, then we have what we call the Young modulus. Young modulus is a ratio between your stress and your strain. Okay, now that will mean F over A over what? E over L in terms of F L over E. Okay, this expression you can keep it. Okay, so this is the point. Now let's briefly about Hooke's law. So Hooke's law is talking about elasticity or the elastic deformation region, where the force applied is proportional to extension. Okay, so the within the elastic region, the force will be proportional to the extension that is within the elastic region. The force applied is equal to extension, the extension created. Okay, the more force you use, the greater extension you are able to cause. That is the Hooke's law. Okay, so basically these ones will help us. But just to say something about sound, if you have molecules which are closely packed, okay, they are able to transmit sound because they are more elastic. Elastic in the sense that when they are displaced, they return back. Okay, so let's say when they are packed like that, when this vibrates, it's able to hit this one easily. This vibrates, it's able to hit the next one. Unlike when you have something like that, and then when you have something like that. So this can be gas, this can be liquid, this can be solid. So see that solids will transmit sound faster than this because these ones are far away. When they vibrate, they may not even touch. Okay, or they will touch a little, but here difficult. Okay, so this tells you why sound will travel faster in a solid than in a liquid than in gas. Okay, right. Same thing when let's say we have air on the surface of the earth, then it's hot. Let's say above it the region is what? Cold. Okay, right. Then there's change in density. Of course, it means the separation hasn't changed. Okay, here closer, here wider apart. So in that case, sound will have a different movement in these two. So at that point, it is faster up, then we can lower down because of the separation. Sound will be conducted in the colder region than in the lower. Okay, so that will tell you why somebody shouts during the day, difficult to hear among people. Maybe at night when the person shouts, is able to travel far and people are able to hear. Okay, so in the night, we have cold air, of course, a little above it. So the air density has changed, and then you have change in terms of sound transmission across. Right. So the point has been emphasized. That is what I wanted to discuss. So I think we have captured this one. We did that in the previous one. Just a recap of that, so that we can move on. Now let's look briefly at the other points that you may also come across, which you can incorporate into your reasoning. So we are trying as much as possible to give you points that you can use to sort of answer questions. Okay. Now let's say I have this molecule. This is my solid. Okay. This is a solid material. Now if I apply force against this, okay, as against that, which one is it likely to break? So that here the resistance will be greater, so it's not likely to break in this direction than in this direction. Okay, so let's say you have fiber, you have molecules along it like that. Then you see that the strength, tensile strength will be greater. If you go this way, it is greater. You need greater force to destroy it than when you go perpendicular to it like that. If you go along the axis, the long axis, you can't go. So it depends on the orientation of the molecules in the material. That is what I'm trying to say, right? And then when you have a molecule like this, as against this, okay, here if you apply force, the molecules have room to move, so they can move a little, but they will not probably break. They move, but not what break. Okay, then such property we say the material is tough. Okay, it can deform, but it will not break. That is means it's tough. And then this one, if you apply, it will not move. It will not move. Okay, but can break. Okay, can break. Okay, such this one, this where it doesn't easily move. On that property alone, doesn't easily move. We will say it is hard. Okay, it's a hard material, very hard material. Some may be that, but can easily break. But some will be able to withstand the force. But unless the force is very great, then before it will cause it to break. Right. So hardness in physics is not equal to toughness. Okay, they are separate things. So rubber, for instance, or plastic, may be tough, but not hard. Okay, but other solid materials may be hard, but not as tough as other materials. Okay, so these are just reasons to let you understand the principles. Okay, right, good. So, for instance, if we have a concrete, we can use concrete and then the iron rods in it to illustrate this. So, if this is my concrete, the molecules are packed, very well packed. Okay, packed. They are packed. Okay. Now, if force is applied here, because it's very hard, it's difficult to break. But as you do that, if you do that here, this is resisting. Now this is trying to move in here. So there's a thing here. This is being stretched. Okay. So there's a tensor kind of tension on it. Okay. It's being stretched. Okay. Now the molecules do not have any place to go. So all that can happen is you can have a split here like that, a crack, and then ultimately this will break. Okay. So it ends up that here is resisting, the force comes transmitted downwards, and then the tensor strength will cause this one to break. Now, so in this case, this is very hard, but it's not what tough. So we can sort of give it toughness, or to be able to withstand force by putting iron rods in. So if you put iron rods in here, the force here, this can expand. So as it goes, it expands and then prevents the concrete from breaking. Okay. Apart from that, if there's crack, it's not able to travel up to cause the whole material to break down because of the shield by the iron rods. Okay. So the shield by the iron rods. Okay. So that is one thing that you can look at in the construction industry. Now let's look at this linear expansivity. So linear expansivity, we can bring that as E here. Is giving us the fraction of the length, the fraction of the length of the metal that expands through a certain given temperature. Okay, so this is heated and it expands by E. Okay, what degree the proportion or the constant or the proportion by which it increases, it increases in length per maybe a degree rise in temperature. Okay, so the linear expansivity will be given by the fraction of the length of the wire. Okay, the fraction of the length of the wire, that is of course that is expanding. So if you want to get that fraction, so it's that fraction of the length. So fraction of the length, which is so the fraction is more or less like my E over my L. Of course, times my L. As you move on. Yeah. So that change, let's say change in length. This can also be mean as the change in length of L of L. Okay, so this fraction of this, that will give us the change times the temperature change. Okay, change in temperature. Okay, which is this, the number of degrees that has gone. Okay, so this whole thing will give you the total E. Okay, the total E that you would have had. So we can replace this E here by this equation. Okay, this equation can be written as my alpha, where this one alpha is equal to the change in length over L. Change in length over L. Okay, so if alpha is equal to change in length over L, then the linear expansivity will be equal to what? My alpha of my L times my change in temperature. This is the formula I want us to put in. So this formula can be substituted in this. This is the Young modulus. Okay, the Young modulus. Okay, this formula can be substituted in this to derive other equations. Now let's assume that how much work is done if you apply force to stretch this over a distance, able to stretch it over a distance E, let's say distance D. How much work is done? How do you calculate that? So we know work done is equal to force times what? Distance in direction of force, in the direction of force. Okay, right. So now if you start, let's assume you are not using constant force. You start with a certain force and end with a certain force. Okay, right. Let's say initial and final in proportion. This is proportional one. Then of course we have to find the average of this force. So it will be F1 plus F2. Okay, something like that. Okay, and then that will be an average too. Now if the forces, let's say the force is the same, in that case this and that, then you're going to have at the end, you're going to have what? This is going to reduce to half the force, the average force. Okay, because change over time, average force times your distance. The distance will be the expansion E. So this will be equal to the energy or work done. This is the formula. Right. This will be the formula. So this is the formula I want us to look at. Right. So in other words, let me just also be clear here. In other words, let's say you have this, okay, and then you are stretching. Initially, the force in it was 0, equal to 0. Now, as you stretch, you come to F. Let's say F here. This F naught, you come to F0 here. Now that's the final tension. You stretch from 0 to F. So see that the average will be F plus F over 2. Of course, this is the starting. Initially it was 0, and of course, work done is the force in that material over that distance, okay? Right, not the force which is pulling, the force that is generated within, the force that is acting on the body over a distance, okay? So this force times the E, and of course this is 0, so we come back to what? Half F times E as the energy. And this is what we have done here. This is the same as what we have done here. So in this case, the initial F that you're talking about is 0 because there's no tension in the wire before stretch. And as you stretch it, final point F. So the average force will be, average is found by adding initial and then the final, divide by 2. And that is how this formula comes about. Now let's look at this illustration. Let's say this is solid. This is solid. Okay. So the arrangement may be in crystals. Okay. Some crystal kind of arrangements. Okay. Like we say, diamond has diamond, and then graphite are all allotropes of carbon. Okay, like a different arrangement. We make one very hard and then one just slip over the other. So let's say this is solid. Okay, and then this is gas, and this liquid. Let's assume this liquid, and then this is gas. Right. So we have something like that. We want to investigate the potential energy, or what we call the mutual potential energy. Between, so at this level, this is either the atom, depending on what material it is, or it may be the molecule. Remember, we defined molecule as the more or less a compound that can exist on its own. Okay, exist on its own. That is molecule. Okay, and then atom is the smallest unit, the smallest unit of the substance, the smallest unit of the substance. Okay, that is, let's leave it at that. When it comes to chemistry, we'll talk about it. But what I want to say is, the smallest unit that can stand on its own within a substance can be an atom or a molecule. In fact, atom sometimes are the molecules because that's a unit that can stand on its own. That means it can exist on its own. Right. Now let's take one. Let's say we take this one and then that one, or this one and that one. Here, we have them here. Let's do some few investigations about this. Okay, we want to find the potential energy. We know potential energy, of course, is the same as the work done, or equivalent to work done proportionality, can come in the form of maybe kinetic energy converted to, and so on. Now, your potential energy usually is by virtue of your position, and then your interaction with the surrounding. Okay, by virtue of your position and interaction, you have some kind of potential energy. Now, every two bodies that you have will have an attraction, will have force of attraction between them, or will have force of repulsion between them. Okay? Yeah. So if we are looking at the potential energy, say potential energy is a form of equivalent to work done, okay, or energy, kind of energy. So that will mean the force implied in the situation, okay, times the distance in the direction of the force, okay. The force implied in the situation times the distance in the direction of the force, or the force within the system times the distance change, right? That is the work done, which is also the equivalent of potential energy. If we are looking at the molecules, if we are looking at the units for this solid or these materials at the molecular level, right? So we know force, we'll come to it, but we have defined force to be proportional to, if you want to find the force between between two bodies here, it is proportional to the product of the masses, the product of the masses of the two bodies, and is inversely proportional to the distance apart, separation. So this distance is r, this m, this small m. Force is defined by this, okay? This is from Newton, when he tried to investigate Kepler's law, and then came out with the inverse square law. Right, so if this is the case, then F, if we convert this to equal sign, then we should have a constant of proportionality here, n over r squared. Okay, now we are saying this for standard distance. So let's say from this, if this is the reference point, this mass moving to this point, the surface of this mass, that distance will be r. That will be defined by this. Now, so in real sense, let's assume that at the level of this one, where we are dealing with very, very small molecules very close together, the exponent of r not known, we can then say force is that force is more or less what we have here, a constant, certain constant a over r to the power what do you call it, let's say p. Okay, right. Now this constant will be multiplied by the distance r. This is representing, let's say, our m here, which is going to be constant in the, because that is going to be the reference point, it's going to be constant throughout. Okay, so this more or less what we have, and that's the force that we have. So this one, of course, we can bring our m and then our r here. So you see that at the end, this r is going to affect this r. Okay. Now, if we want to multiply by, if we are finding the force per unit per mass, then we end up dividing here also by m, and this small m is going to cancel this. So, in essence, what I'm trying to say is you have F to be more or less this no longer, because you multiply by distance, is now work done. Okay, it's now work done. So without this is the work done. Okay, we are having something like that as the work done. Okay, now this can be written as K I M I P minus 1, something like this. Okay, now this is the work done. Now if we want the potential that exists within this space of work done. Okay, potential is usually the work done per unit mass. Okay, unit mass. So if you divide this by mass, then you're going to have K over R P1. Now you agree with me that P minus 1 will be a constant, or will be a variable depending on whichever, sorry, not a constant, will be a variable depending on whichever materials you are dealing with. Okay, so this is a constant. So we can express this one, or we can let another variable represent this one, say K over R, let's say N, something like that. Right, so that is the potential. Okay, so from this formula, then we can see that the potential between these two, V, one potential is attraction, so that is going to be positive. K, let's say the K be A over R to the power M. Okay, now this is representing, because we have divided by this is the potential at that point. Of course, the other kind of force between the two is repulsion. So let's assume repulsion, because this one is, we have indicated attraction as positive, repulsion is going to be negative. And then that is also going to come with the same formula like this. Let's say that one B over Rn, something like this. Okay, so you see that this will represent the mutual potential difference between the two bodies, the two molecules, or the two units at the molecular level. This will represent that. So some textbooks will just use, so it depends on the notations that you are using. Some textbooks will use A is equal to A over Rp minus B over Rq. Okay, so the same thing. Right, so it comes back to the same thing. And there's the point I wanted us to do. So depending on the material, these ones may have certain factors. Maybe one is by factor 10, maybe for a particular material. The constant given to you is by 10 or 9 or something. And then this ratio is given as 9, this is given as this, maybe A, or maybe given a certain constant. Then you put them the values, and then you'll be able to calculate at the molecular level the potential energy and the potential between two bodies, the potential that exists between two bodies there in terms of energy. That's referring to potential. One thing I want you to remember is just a recap of this so that you get a concept. Usually we have force. Okay, we can start with something like this. Let's assume this is a positive one. So this is the body. Let's say this is a charge, okay? A charge. For this reason, that is one thing, okay? This charge have lines of forces, okay? Lines, forces, okay? Have lines of forces. Some will say, example is flux, okay? Flux, okay? Now these lines of forces, we can make it over an area, and that becomes flux gauging, flux density, okay? So this can be an area over an area, that will be flux density. So this is flux density. Because then you can come to the force itself, okay? So in that order. So in the same sense, you can have lines of forces or lines of strength. The lines of strength will be there, as in. And then the lines of strength over area will become what? The potential, the intensity. Okay, right? The intensity, right? And then beyond that, you can have the actual force itself coming into place. Okay, so you can think about it this way: lines first, lines over area, okay, right? And then the force itself, the force itself. Okay, so with these three concepts, you will be applying them in the next chapter. So that's why I'm bringing this one in, so that you will see that the general concept like this. You have the lines, the intensity or potential, depending on which one we are dealing with. And then of course we have force itself, okay, and then we have work done or energy. This is how I want you to think when we go to the next level. So we are looking at the lines of forces, the lines of forces over area, that's intensity or potential, or lines of forces over, depending on maybe energy over area. This is usually divided by certain, either by an area or by mass, okay, or by distance, something like that, okay. So these are the point. So somebody will say you can put in between the density. So the density is usually maybe by area, the intensity is by distance or by mass. I'm just giving a general concept so that when we go to the next one, of course the force itself is given by proportionality, okay, product of the masses over R, or product of the charges over R squared, okay, if they are big bodies, okay. And then the work done, of course, we know is force times the distance in the direction of the force, okay. Note it, distance in the direction of the force. So the force in the system over the distance, for the distance that the force is able to effect change, that will be the work done. So this general principle